All right, hello and welcome to Differential Equations. Today, our goals are to get some basic definitions and concepts down so that we are set up to understand the language of differential equations as we move through. We want to learn how. We want to figure out what a solution actually is to a differential equation. It's different than other equations you've solved up until now. We'll look at some basic examples, but the first thing I want to do is show you why we would study these in the first place. Now, we're not going to do a ton of modeling per se in this class. We're going to be mainly focusing on the methods and techniques of solving differential equations, the insights into the mathematical perspective. I'm a mathematician, not a physicist or an engineer, but I think there's some really cool just motivation that comes from the world that I'll give you here that will kind of pepper through the course. Um, but anyways, I'll show you these two quick examples in order to just demonstrate the universality of differential equations, why they're so important, why it's like a new set of glasses that you didn't really know you needed. Okay, so let's start with those because I think they're interesting and fun, and then we'll get into definitions and what a solution is, etc., so that you're set up for your homework and the rest of the course. All right, so let's dive right in. Okay, so again, I'm going to show you why we might care about differential equations by giving you two quick worldly examples. So the first example, I'm going to go through this pretty quickly. Normally I do a little back and forth with the class. Not really possible in an asynchronous video, but that's totally fine. Let's build a model for sprinting. And what I'll be basically doing is building a simplified version of what's called the Hill-Keller model. This isn't just like, your math teacher made this thing up on Planet Calculus. This is an actual model of a sprinter. So if we think of a very, very simple sprinting situation, amazing picture, Mally. Thank you very much. You've got a sprinter running horizontally on a track. Okay, so this is his velocity vector here. We'll do a lot of simplifying of what's actually happening, right? Somebody running on a track obviously have side-to-side forces on them, but we're going to ignore that and just think about, the forces that act in this forward and backward direction. We can ignore things like gravity, right? Because we can just ignore it. It's not a part of our model necessarily since everybody's subject to the same thing. So we just want to keep it this single dimension of moving back and forth. Okay. So one thing that we can do to build a model for sprinting, what that really means is we want to have something that predicts someone's position at time t, right? So time would be our independent variable. We're hoping to get to something from position, but what we might have is like maybe just the rate of change, or we have some snapshots of the data, but maybe that's not totally predictive as a filling in the gaps for interpolating data, predicting data in the future. So anyway, what's usually easier to work with, and this is somewhat of a theme, is the rate of change. So if you have something that describes the rate of change, then you can, build the actual present value function later on. So let's think about the forces on the runner. And again, we're only thinking in these two directions. Well, the forces could be described in maybe two categories, FP and FR, where we have the propulsive forces, what's driving them forward, and the resistive force, of what's not allowing them to go infinitely fast, right? So there's a few different ways to conjure up these forces. But you might think of propulsive force as being that runner's own snap from conditioning, their kind of max effort. This could come again, comes from training, comes from genetics, it comes from all sorts of things, form. but this is going to be dependent on the runner. It depends on the runner. So, me versus Usain Bolt is going to be a wildly different F sub P. Um, and same for resistive forces. Resistive forces are things like, the wind resistance. You've got, the body's own limitations. You can only really run so fast. Um, things like, friction against the ground, perhaps, but maybe that's even a bit too granular and not really in this back and forth direction. But anyways, we can break them into these two groups since we're just thinking linearly. So propulsive and resistive. So let's maybe describe each of these things. FP, what do we know about force? Well, we know force is mass times acceleration. And that acceleration, since we said it's going to be dependent on each runner, and the mass is just the mass of the runner themselves, let's simplify that and call it some constant p, which we know will be, again, relatively constant for a, let's say, competition runner. That on any given day they show up and they're relatively going to be performing the same as they normally do. This would be their like max effort, and that will describe the force. Again, you can think here of the units. It's kilograms for mass times, well, for P, the units must be meters per second squared. And then your resistive force as well would be, let's think about it. It's going to be proportional to velocity and the mass. And in particular, proportional to the velocity in the opposite direction. Opposite direction. Because, this pen's goofing up on me here. You can think of, the fact that you're running faster means you're going to be up against more of that force against you, whether it's your own physical limitations, it's wind resistance, but it's going to be proportional to velocity and mass. The one way that we can represent this is using the negative sign because of the opposite direction. Some proportionality constant, we usually use K, times the mass times the velocity of the runner, which we know is a function of time. Okay, so we've got here a nice, easy to understand expression for the resistive force. Here's something for the propulsive force. When we get back to the total forces on the runner of Fp plus Fr, we're looking at Mp minus Kmv of t. So this is nice, and if we break down F even further, we know that the total force will also be mass times acceleration. And so another thing that we notice just representing this algebraically is that the mass will actually cancel out, which seems both crazy and also makes a lot of sense that it would stand independent of the runner themselves. But still interesting that we can kind of just drop that out. So what we get is that the acceleration is equal to that propulsive constant minus some constant times the velocity that they're running in. So that opposite force moving against them. And if you recall from Calc 1, what is acceleration? If velocity is a function of time, acceleration is the derivative of velocity. So we've got dv dt equals p minus k times v of t. What we have is our first differential equation. And the reason it's a differential equation is because it relates the quantity that we care about, in this case, the velocity, to its own rate of change. Okay, I'll get into the details of what we mean by that in a little bit, but I just wanted to show you a quick and easy way that just through kind of plain speak and some pretty simple assumptions, we can model a situation with a differential equation. And this is really their power. It's much easier to do this since we're able to play with derivatives. Okay. Now, I went through that pretty quickly, and I'm going to do the same with our second example, but the power really lies in comparing the two. Okay. Look at a second example. I'll set this up. Okay, so the second example is using medicine delivery to the inner ear. Wild departure from what we were just doing, and there's a point to that. So, about 5% of the world experiences hearing loss. So this is a pretty ubiquitous problem worthy of investigation. So having a good model for what happens inside the ear is important. And so here the basic problem is to deliver drugs to the inner ear is complicated because you need to maintain a constant volume and pressure inside the compartment of what's called the cochlea. Okay, so if this is like your inner ear, you visualize this as a simple chamber. We need to make sure that what's in here remains constant. You can't just pump in fluid and oversaturate it or vice versa, drain it out. So we need the rate of the fluid in to be the same as the rate out. So you have this little device that's, delivering the medicine solution to this chamber. We need that rate going in to be the same rate going out. So the question is, if we're going to deliver medicine to the inner ear, we need something that models the amount of medicine at any given point. Well, we can be certain of how much is going in to the ear. We'll call that A1 in micrograms. And we don't really know how much is leaving. We assume a non-zero amount, but that will be part of the model, right? This is the outflow and the inflow. Here's the cochlea. And so if we're talking about a system that's evolving over time, which is very much in the world of differential equations, a system that's evolving over time, then we're interested in the change in the drug amount within the ear. So what would that be? Well, that would be the amount that is coming in minus the amount that's leaving, right? That's the important amount because that's how much is actually sticking around to deliver the healing properties of the medicine. Okay, so delta A, change in A, is A1 minus A2, right? So A1 minus A2 over some unit change in time, which we remember as being like the average rate of change. We can also think of this as A1 over delta T minus A2 over delta T. And we can take delta T going to 0, shrinking that time window down using the power of calculus to get down to instantaneous rate of change. The instantaneous rate of change, again, that's calculus, that's the derivative of A, is going to be the instantaneous rate of change of the drug entering, is our A1, minus instantaneous rate of change of drug leaving. And this is just a really good solution tactic in general for talking about the rate of change of something that where there's an in and out. It's going to be the net of the two differences of the rate of the drug entering, drug leaving, or whatever the thing might be. It might not be medicine. So if we let U of t be the unknown amount, in the ear that we care about, and we know that R is the flow rate, okay, and that the fluid has a concentration which might be, micrograms per milliliters of the fluid. The flow rate would be milliliters per minute, or microliters per minute, I'm sorry. And the amount of the drug is going to be in micrograms. This will just help us keep track of the units in the model. And what do we see? Using this idea of the derivative of the drug entering minus the derivative of the drug leaving, using these parameters that we just lined up here, then u prime of t, which we said what does that mean? Okay, u prime would be the amount of the drug changing in the ear, since it's u prime. The amount of the drug changing in the ear is equal to the instantaneous rate of change of the drug entering. Now, here's where we use concentration and flow rate, because we don't really know how much is coming in since it's within a solution. But we do know how much is coming in as long as we know the concentration. Okay, so the way that we get around that is by using R, the flow rate, times C1. Think about what the units would be here. This is kind of the magic bullet to this problem, is it's micrograms, it's microliters per minute times micrograms per microliter. So you can see now we've got micrograms per minute, which is what we wanted. Okay. I'm actually going to erase this out so we can just look at the model itself. So RC1 minus, and then for the rate out, it's going to be the rate over the volume of the total inner ear times U of t. Now we'll pause and think about this for a second, why that's the case. So we know that we've got an outward flow of R, microliters per minute. So that's why this is maybe that minus R we're seeing. V is the volume of the entire amount, okay? And or the entire inner ear here. So V is like how much fluid is in this entire chamber. And so R over V is giving you what? The units of microliters per minute all over microliters. And so that reduces to just the units of 1 over minutes, right, or frequency, times the amount of the drug itself, which is micrograms. Okay, and so now our units kind of resolve here. And another way you can think about this is just how much U of t, how much of the drug is in the chamber. That concentration is going to be U of t over V, right? There's a concentration coming in, then there's this unknown concentration in the ear that we care about. That's U over V, and that's where we get that from. Okay. So, and again, I'm cruising through this. You are welcome to pause, rewind, ask questions, all sorts of stuff. Obviously, in the discussion, not in the comments of the video or whatever. So, this is the model we've got: rate in minus rate out. And what we have, if we maybe write it like this, RC1 minus R over V U of t is another differential equation that models this situation, again, pretty reasonably. There's a lot of assumptions, there's a lot of simplifications, but in general, these are both pretty accurate to what's going on. Now, let's compare for a moment. This is really what's, I think, really powerful and interesting, is that, all right, we've got that u prime was some function of time and that unknown amount, which we saw was RC1. Those are both constants, minus R over V. That's a constant, times U of t. And we had from the sprinting model, V prime was a function of time and velocity, because it was what? That propulsive effort, which was a constant, minus K, which is a constant, times V of t, which is that unknown quantity. So what we have here, what I'm trying to show you, is that you have two functions of the form y prime equals a plus by. The rate of change of the function equals some constant times the amount that you care about. This is what we call a linear first order ordinary differential equation. I'll explain why we know that it has all those properties later. But right now, what you should know is that we just modeled two completely different scenarios with none of the same assumptions, really. And you have the same exact equation, which means that how we solve these equations, how we come up with a solution to this equation, will be exactly the same regardless of the context. Okay? So that's pretty wild. The math that governs someone sprinting versus how we deliver drugs to an inner ear are the same. Okay. So that's hopefully pretty interesting and enough to spark some interest into why these things might be valuable. The fact that they're so universal, it just it blows my mind. You can probably tell just by the way I'm talking. So what I want to do now, there's a bunch of other examples I could go into here, and I won't. But what I want to go into now are the basic principles, concepts, and definitions you're going to need to study these things. I just said the solution that we're looking for. You don't really know what a solution looks like yet to a differential equation. We'll talk about that and a few other things to set you up for the homework and for the rest of this week. But let's pause here for a moment while I get those set up for you. All right. So, first of all, what is a differential equation and what is a solution to a differential equation? So, we know what an equation is. Relating some left-hand side to a right-hand side, you just hope there's some sort of truth value there. You're used to solving static equations, which means something that has a fixed number that we're after. But that's very different from the form of the differential equation I gave you. Say this y prime equals a plus by. Okay, what we have is y prime is some function of x and y on the right hand side. And it's implicit that y is some function of x. This is just one example of a DE, but the idea that is inherent here is that it's an equation that relates an unknown quantity to its derivatives, plural. Here, I've given you just the first derivative, but we can go to whatever order derivative we'd like. Second derivative, third derivative, and so on. We won't be messing with much stuff beyond the second derivative, maybe with a few examples just show that we can do it. But outside of the second order derivative, we really, there's very few applications that would matter. So it's an equation that relates unknown quantity to its derivatives or a function to its own derivatives. Okay. So if it's an equation of a function that relates to its derivatives, then a solution is a family of functions. Okay. So in other words, what would be the solution to a problem that relates a function to its derivatives, an unknown function to its derivatives? It would be a function. Okay. And so the simplest and most important DE, and we'll be studying it and using it all semester, is this one right here. Y prime equals ky. A little bit simpler than the one we were using in our models. Y prime equals ky. K is a constant. So what does this say? This says that the derivative is equal to some constant times the function itself. And, if I played the Jeopardy music here for a few seconds, you would hopefully be able to come up with the solution to this because we kind of hit you over the head with it in Calc 1. We say, what has its own derivative times a constant? What function has its derivative as itself times some constant, right? Self times some constant. And what that would be y equals e to the kt. And if that didn't ring a bell for you, that's okay. Don't beat yourself up too much, but you definitely want to remember this and park this in your memory. This is one of the most important solutions to this DE that we have. And so the reason is because if we take a look at this maybe in a different way, dy dx equals ky. And then we rewrite this by what we call separating variables. So I multiply both sides by dx and I divide by y. I get dy over y equals k dx. And then what we can do is integrate both sides. And we'll get the natural log of y, absolute value of y, is equal to kx plus c. And I have run out of room, so I'll bring this over here. All right. And then again, our goal is to hopefully solve for y. It's locked within a absolute value sign here. We can go ahead and drop that absolute value. Well, let's not do that quite yet. What we can do is raise both sides as powers of e. We know to do to get rid of that ln. And so what we will get here, once that ln drops out, we'll get the absolute value of y equals e to the kx plus c. Remember some exponent rules here, right? This is really e to the kx times e to the c, a constant of integration. This is going to be playing a bigger role in this course. Sometimes it can get kind of trivialized in calculus. It's going to be a big part of this course because the constant determines the solution. So we can also say that e to the c, since c is any old constant, we can just call that c. So we'll call this c e to the kx. Okay. So what we have right now is that the absolute value of y equals c e to the kx. And again, since c is any old constant, then plus or minus doesn't quite matter, and that's why we can drop that absolute value sign and just say, all right, well, plus or minus c e to the kx is just c e to the kx. C encapsulates all real numbers, unless we have some other restriction, which we don't. So what we have is y equals c e to the kx is a solution to what we call is the general solution to y prime equals ky. So this is a very different solution to an integral or to an equation that you might be used to. We're used to looking for a number. Here we're looking for a function that solves the relationship. So you might not have seen an exponential function kind of popping out of here as your solution, but this is the way in which we do it. So this first method that we'll look at is what's called separable equations, doing exactly what I did, which is breaking the variables into both sides of the equation and then using integration to solve, and then, a bunch of algebra. But that's the first and most important solution to a DE, all right? I'm going to give you some particulars here as well, which is that a solution to a differential equation is a function, in general, is a function that satisfies the DE, like we saw before, and is defined and is continuous on an open interval. This is an important piece because you can get some just algebraic weirdness. Excuse my voice. You can get some just algebraic weirdness where you can get things that solve the equation, or it's just what we call the trivial solution, which is just y equals 0 would also solve this, right? The 0 function would solve this equation. But that doesn't really help us at all. So we discard that. But then there's also some weird algebraic things that can pop up that might solve your equation, but they're not defined at an open interval. Okay. So we need to be very kind of particular about our language, what we're after. We care about an open interval because, again, we're looking for maybe a range of measurements where this model works, a window of time where this model works, right? It just lasts for one point in time, that it doesn't really do anything for us because differential equations are about predicting how systems evolve over time. All right, so you have what a DE is, you have what a solution to a DE is. Now let's go into classifying some more DEs, so some more terms. The idea of linear versus nonlinear. We'll be focusing mainly on linear differential equations, but we will play with some nonlinear ones. Nonlinear ones are much, much harder. Linear does not mean that it's just a line. It means linear in the sense that the parameters or the coefficients of the derivatives and the functions in the DE are first order or first power. Okay. So what this means is linear in y and its derivatives. Okay, so, y, y prime, y double prime, all first power, what that means. And again, the coefficients of this, as I said, also first power in y. So like you could have what I was saying before, you could have something like y squared times y prime. And this in itself would be nonlinear because of the squared and the y over here. But also, you had something like y times y prime. This kind of breaks this definition of linear as well. So if I had y times y prime plus, xy double prime equals 0, something like this. This is actually nonlinear because this term in itself is not linear in y and its derivatives because you have this first power of y times its own derivative. So that is actually technically nonlinear. All right. So nonlinear means just, not that. So things like y squared, things like, I'll put this maybe over here in this category. Things like y squared plus y double prime equals 0. This is not linear because of this y squared, not because of the second derivative here. Okay, so that's what we mean by linear and nonlinear. So the ones that we studied up above, like y prime equals a plus by, and v prime equals p minus kv, these are all linear differential equations, okay, because they are linear in y and its derivatives or v and its derivatives. Those all have first power, and their coefficients are not the dependent variable. All right. Some other things. So that's linear versus nonlinear. You'll have some practice problems with that. The order of a differential equation. Order is, in this context, the highest derivative that appears. Okay, so it kind of tells us how dialed into the rates of change are we getting here. So, in other words, for this guy, this is a first order equation. If you think of this in a physics context, it means we're only dealing with velocity. For, something like this would be a second order equation because we've got a second derivative showing up here. All right. And similarly, if we got y triple prime plus y double prime plus y prime, this would be a third order equation. And so you can kind of quiz yourself of, all right, this is a third order equation. Is it linear? Yes, it is, because it's linear in y and its derivatives. So it's also linear. Same with all of these. They've all been linear. But how about something like this? If I had y squared y double prime plus xy prime plus x squared y triple prime. Something like this, we'd see, all right, the order of this equation, order is 3. That's the highest derivative. Is it linear? No, it's not, right? Because of, well, I showed you this right here is breaking that. It's not linear in y and its derivatives. Okay. So we have the ideas of linearity and order of differential equations. All right, this is going to help us break it into categories. The reason that we need all these kind of classifications is because since we're looking for families of functions, how we solve them will be really like context specific, meaning it's just going to depend. So what method we employ is going to depend highly on just kind of the setup, right? What pieces do we have in play? Is it linear, nonlinear, the first order, second order, third order? That's all going to matter a great deal. Okay, so that's why we need to uh, frame these up now so that we start to become very familiar with them, so we know when we're looking at an equation what it is we actually need to do or what would be appropriate. We have another concept important starting off, which is that of a general solution versus an initial value problem. Or aka in terms of the solution, we'd be talking a particular solution. Okay. There's actually quite a bit I could say about the terminology around what we call solutions in this course and how it's tragically confusing. So don't get too hung up on it. But what I do want you to know is that for a general solution, this means we're really only unique up to C, constant of integration. Okay, it's really a family of functions. Whereas for an initial value problem, this is a one specific function. So an initial value problem means I've given you a point which fixes the problem with a value pair. Okay, so a general solution, I just gave you an example of it for, y prime equals ky. We know the solution y equals c e to the kx is the general solution. Why that's the case is that for any value of c, this will work. And we'll verify solutions in a bit. I'll show you how to do that. It's not that difficult. But for over here, for an initial value problem, we're given a value pair that will pin it in place. So in particular, let's say I've got one like y prime equals 7x squared. But you're given the fact that we know that y of 0, kind of think of this as like, all right, this is the starting position of this thing. When t equals 0, y was at 4. This could be velocity. This could be, again, whatever, how much drug is in the ear. And so if we go to solve this, giving you the method we saw before, separate variables. And this might have been something that you've done in Calc 2, hopefully maybe a little bit. Integrate both sides. Integral of dy equals the integral of 7x squared dx. So we get y equals, 7/3 x cubed plus c. And again, we really had constants of integration on both sides, but we collapsed that into 1 on the right. That's actually a 3. And so this is what we'd call the general solution, right? However, we're looking not for a family of functions, not for all of these cubics that do this, but for one in particular, one where y of 0 equals 4. So y of 0 equals 4, which we call the initial conditions. the initial value. Give us that 4 must equal 7/3 times 0 cubed plus c, which tells us that c equals 4. Therefore, our particular solution that we're after is y of x equals 7/3 x cubed plus 4. So when we solve the differential equation to start with, we get a general solution that's only unique up to a constant. It's a family of functions, but if we have an initial condition, starting point, whatever it is, then we go and find this is that one singular curve that solves it. Okay? All right, and lastly is how do we verify solutions to differential equations? Something you'll have practice with in the homework. It's really plug and chug. I won't lie to you. Okay. As long as you understand your basic calculus rules, you should be good to go. I highly recommend reviewing integration and differentiation now, whether it be on Khan Academy, flipping through your Calc 1 and 2 notes. If you've recently taken Calc 2, that's great. That's ideal. If you haven't taken it in a while, that's okay, but you're going to want to review that stuff. So let's do a quick example here where we might see, verify that a given function is a solution to a differential equation. Because as you've seen, it can vary. It can be completely different situations. So show that this is a solution to the equation 4x squared y double prime plus 12xy prime plus 3y equals 0. Actually, what I'll do is quiz you a little bit here, okay? So hit pause. You kind of got to play along here. Hit pause after I finish asking you the question. What type of differential equation is this? All right, so if you need a hint, is it linear? And what order is it? So it is linear because y and all of its derivatives are of the first power. You say, but Mally, got an x squared over here. Yep, but that's the independent variable, right? So it has to be linear in y and its derivatives. So this actually is linear. And it is second order. Why? Because the highest derivative you see is the second derivative. You don't need check marks. It's not like this is checking any boxes. It's just we went over them. Okay. So this is the DE. We want to verify that this is the solution to this. So what you will need is, remember, all right, well, if we're saying this is y, I'll be plugging that in here, but I'll need y prime and I'll need y double prime as well. So if y is x to the minus 3 halves, and y prime must be negative 3 halves x to the minus 5 halves. Y double prime must be, what is that, 15 fourths x to the negative 7 halves, right? So then to check and see, is this a solution to our DE? We simply plug it in and verify. So 15 over 4 x to the minus 7 halves plus 12x y prime we said was negative 3 halves x to the minus 5 halves plus 3 times y, which we said was x to the minus 3 halves. Again, here's a place where you don't know how they came up with the solution, and that's actually, we wouldn't be able to solve this for a couple weeks in this course. We're just verifying, does this work for this equation? And so we punch through the algebra here. All right, the 4's cancel. That's nice. X squared is really 4 halves. Right, x squared is really 4 halves. So x to the 4 halves, x to the negative 7 halves, we get what? 15 x to the minus 3 halves. Here the 2 cancels with 6 here. So we've got x to the 2 halves times x to the negative 5 halves. So we get negative 18 x to the minus 3 halves, and then plus 3x to the minus 3 halves. Is this equal to 0? Why, yes, it is. That checks out. So yes, y of x equals x to the minus 3 halves is a solution. Now we can't say it's the general solution, right? Because it's not constant. This is a particular solution. So you might even say particular solution. Right, which again just means it works. There's probably more that work too, but this is one that works. This is how you check it. You need to, when given the function that you're testing, find its derivatives, substitute in, and make sure it all zeroes out. Okay? So I think we've covered our goals for the day, which were give you some motivation on why to study differential equations. It's this language that it's easy to model situations, easier than maybe just coming up with them statically, okay? Because we can talk about rates and the quantities a little bit more hand wavy and still come up with stuff that works. And the math is the same for wildly different scenarios. Again, that is the crazy part. What are solutions? We know that solutions are functions. Difference between a general and particular solution. The definitions and basic concepts we came up with, and what separable equations is that method that I showed you of splitting up the y terms and the x terms, or the t terms and the v terms, whatever it might be. Your dependent and independent variable are on separate sides of the equation, which was possible for some of these, like this guy, but not possible for other ones. Like here, I would not be able to split up the x and y terms completely on either side. So this is not separable. Okay. So I hope you found this helpful and informative. This is a little bit on the longer side, but that's okay. It's day 1, and I'm looking forward to working with you, seeing all your questions in the class discussion. Again, I expect that kind of big whiteboard to be our hub of where we're working on problems together. Practice is going to be indispensable in this course. So wish you well. We'll see you next time.